Hello, welcome back. So this time we're going to be putting most everything together and even a couple things that I left out, like rank on purpose, so that we can kind of go over them intuitively now. And what we should note is that the Graham-Schmidt process is an algorithm for converting a list of linearly independent vectors into a list of mutually orthogonal vectors. And orthogonal means at 90 degrees. So these three, in this case, bases, are going to be mutually orthogonal or orthonormal vectors. And orthonormal is just stands for unit vector. And when we think of orthonormal or a normalized vector, we think of something that is of length 1. So when we say an orthonormal basis, we are talking about a of length 1. And it is just a way of measuring the magnitude or the scale of a vector. And we'll see that later in the process. And on the right hand side, we have Python running. And on the left hand side, we have my work I've already done. And we'll step through it and kind of translate the math on the left onto the right hand side using SymPy. Now, you can use things like if you wanted to create an array of uh, NumPy, you could certainly do this, and this would work. We are using Jupyter notebooks. The problem is that this doesn't look too nice. So instead of doing something like this, what I thought would be more beneficial, or even doing a list just like this, and this would match on the left-hand side what we have. Instead of even doing this, what we can then do is something like this, where we have SymPy printing it out nicely for us. So I thought this would be a really nice treat, and since we already did some of the octaves, some of these commands will even be familiar just typing this out, and then we can just use SymPy to convert it, and SymPy would even accept a NumPy array as well. So moving on, the idea is that we want to take these vectors in this set, and what we want to do is make sure that they're, first of all, that they are independent, that they are linearly independent, and that one does not span the other such that there is linear dependency. And then we could only have maybe two out of three basis vectors, because let's say that this vector were 8, 10, and 12. This would be and as we saw in one of the previous videos, we saw that this would be a multiple and a scalar multiple, and we see that this would become a problem, and that we would only have two out of the three vectors in our basis vector. So if we want to check that these are mutually linearly independent, what we can do is what we saw is do RREF, and we can take a look at some of the columns here. I've already written some of the code out for us just in the sake of time. And what we've done is we've taken this and we've reduced row echelon form, and luckily enough, it's given us the identity matrix. And of course, we know that the identity matrix has row and column. And this is also something we should be interested of. We should take note of this. It not only has column orthogonality, but it also has row orthogonality. Huh. We should really pay attention to this later on, and we'll even go over why this is later. And so what we see is that this is going to be separable. And how do we know this? If we take the dot product, what we should get is 0 by definition of linear independence. And we do. And so what we want to do is then look at the rank. The rank is simply the quantity of linearly independent rows. And we see that there are 1, 2, 3 linearly independent rows. So this is a really cool, quick catch up and refresher, and some syntax really quick. We're not really going to be using this too much. We are not going to be using this. If we want to look at these now examples without using the identity vector. This was just, the identity matrix. This was just to show you that these are linearly independent by definition. And we can just see that, they're not really easily obtainable. So what we want to do is form a basis. And the way that we do that is we're going to take this first one and form a basis. We're going to just call this V1, and we can actually even call this Q1. And it's nice because it has 1, 0, 0. If this were all zeros, I wouldn't really like that. So be careful of that, as well as the multiples as well. You can get A back up here so we know what we're working with. And I'm going to get out of this. And what we want to do is we want to create these, and instead of doing this ugly slicing, by the way, this is called slicing in Python, and all I'm doing is basically taking each individual row, and column, excuse me. So I'm saying from this row to this row, so basically all rows at the first column. And the first in Python, and basically any programming language that you're going to encounter, the indices are numbered starting with 0. So you would get this, and if we go through A2, you would get the second one. Obviously it's now believing that this is here, and we would see this. So this is a good example. In A3, I'm thinking it would give me the last one. And this is how you would do this. So to give us A, we have this guy. And instead of doing that ugly slicing, what we can do instead is this. We can basically just, SymPy will let us access the columns just like this. And to prove to you that this is real, I can just, here we go, U1, U2. And it's literally the same thing as slicing. So I'll go through and show you a couple different ways. And actually, we're going to go step by step through how to get all of these mathematically, and then at the end I will show you that SymPy actually has a lot of these functions. But we're going to use this, since we did this by hand, and I haven't looked, but I'm sure there is a projection function. But as we can see, this is going to be a projection. And basically a projection is just going to eliminate and subtract out one of the orthogonal positions out of the vector. And how we're going to do this is we're going to just set this up, and we're going to say, okay, I'm going to take the first orthogonal column, the first basis, and I want to set it to be this Q1. And this is going to start our new basis. We're going to start our new basis from A. So we can say that A is now in terms of this basis. And for every one that we need to figure out, we can subtract off this new basis that we would see in purple. And we'll see that in the next step. And so to subtract this out, just take the dot product of this with this first basis vector in the direction of this basis vector. So that will give us 2, 0, 3 minus the dot product, which is a magnitude, it's a length in the direction of V1, which we see right here. And we have this as Q1 over here, just for the record. And we're saying it's Q1 because we're starting this new basis. And we see that performing this is equivalent to, all right, so let's get it back up. Doing something like, this is, we're going to call Q2 prime is going to be equal to U2 minus U2 dotted with Q1, which is the first basis vector, times our first basis vector. And let's look at what Q2 prime is. Nice. So this is an orthogonal vector, and we see that right here as well. This is an orthogonal vector, but be aware it is not an orthonormal vector. Remember, when we hear a unit vector, what we should think of is a particular direction and a particular magnitude or a particular length. And the way that we find length or magnitude is simply going to be in this denominator here by the distance formula. And so this Q2, this Q prime is, this Q2 prime is actually just the orthogonal. What we actually want is the orthonormal. And to find that, what we need to do, actually what we should probably say is this magnitude, and just to show that this actually does exist, 1/3. And that's exactly what this would come out to. And instead of, keeping the vector out here, here's a tip. Move it off to the side and keep this as a scalar. That's why I highlighted up here to you before to remind you that, hey, this is just a scalar of this. And we're using this dot product to basically get this length, almost this scalar value of how much this thing is going to be stretched. And we can see that doing this Q2 would be just the magnitude of this times the prime. And to check that, that's perfect. And so we can say that the scalar, here's a way that we could now use some of the built-in library functions with SymPy to check this. We can say that the scalar for this is going to be, we can say that the norm of it is 3 now. And we do that with the norm. And if we want to recalculate using this scalar, but we've just calculated it a different way, saying 1 over, which is what we see right here. We see 1 over this scalar value, which will give us 1/3. And so this is this is why I say don't always rely on these library functions to calculate this for you. This is really cool, but really what we're doing is already seeing that. It's a little bit harder to see if you don't already just know in your head that this is the square root distance formula, and to say, okay, I don't even need to really do this. This is just 0 squared plus 3 squared is 9, and then take it's 1/3. So and I just have gotten used to writing this as a vector times a scalar. And so that's exactly what we have. And at the end of the day, we get this Q2 vector, and that's exactly what we needed to get the orthonormal to this other one that we have. And we're going to do the exact same thing to get the third one, and I'll show you what that looks like. And the way that we do that is we take the third basis and we subtract out the comparison between the third and the first, and you can see that. And that's the distance in the direction of, and then we subtract out the comparison between the third and the second, that Q that we just did. And we can use this and call this Q1. I just did not, just so you can see that it is coming from this original assignment, but we absolutely are going to use Q1 as well. And so we say, okay, let's assign Q2 to V2 just in case we want to use it. And you can see Q3 prime, we have to work on the prime first because we want to find orthogonal and normalized unit vector. And so we do that by taking this and subtracting it out, the third and the first, and see we've used Q1. Over here, we just use V1 to show clarity that this is with respect to the original basis in our new basis. But it comes from, I showed you the link, our original basis. And this, now we need an orthogonal basis with respect to this one. And so we do the dot product with the third and the second, and we get this Q3 prime. And so this is the orthogonal vector now. And so it's independent to both columns in the basis, and we see that. And if it weren't, we wouldn't be able to, again, put this in the Q, the orthogonal matrix. And we see that we get 0, 5, 0. And to normalize this, we just call this function. We're just going to call the function for now, and we're not going to go through the manual calculation of this again. This is something that will save you because you don't want to keep having. You see how long now this Jupyter notebook gets? Obviously, this is running in a Jupyter notebook just to show as a demo, but if this were a program, this would be called as a function. And if they already have this function written for us in this library, that's awesome. We can just call normalized and get the normalized library. Now, what we need to do is put all these vectors into a matrix. And unfortunately, it's going to be hard to do that. It's going to be hard to add the rows like we would normally, and that we can intuitively, just like we can add and stack rows onto each other. But a computer is going to have a hard time doing this. So I'm going to take the transpose of each one of these, and I'm going to put them together myself. So I want these to all be one matrix. And the way that I can do that is to transpose each vector into a 1 by 3, and then I can put them together and call and create this now orthogonal matrix that has all of and these are the prime ones. Remember, I just did this so we can see that has all of these. And now doing this, I can put all of them together, and this is these are the orthonormal, excuse me. These are the orthonormal vectors that we see in here. And to keep going now, what we can do is we can actually show that there is, instead of going through all of this, what we can actually do, and this is great. By the way, we're finished the Graham-Schmidt process. The Graham-Schmidt process just says find an orthogonal basis. And we did that step by step by step. But the cool part is that we can actually call a function inside of here, and we can return a matrix from Graham-Schmidt. And what we want is to pass in our unit vectors 1 and u2 and u3. And what we want to say is that these are orthonormal. And we're going to call true. And what this is going to do is actually just calculate it for us anyway. So you can see that our manually created match the SymPy calculation, which is really cool. And now what we can do is actually go one step further since we're already here. Now that we've proven and we've done the manual calculation, going through all the math on the left-hand side here, and then I showed you some library functions and called them to make a couple of these steps simpler, and just basically calling this Graham-Schmidt function. So now my other question is, now that we've found Q, we should probably take a look at what the orthonormal version or what the normalized version of A is. If you recall, it's actually just going to be the identity matrix. And that is because each column and subsequently each row is linearly independent. They are all mutually orthogonal, and Q is mutually orthogonal and orthonormal more specifically. They both are. And it's interesting because we can think that we can actually get from A to Q and vice versa from Q to R. And all we would need to do is a simple row swap. And actually, that's a formula that is very important in understanding the next part, that the column space in the rank and is the same as the row space. We can see that each is 1, 2, 3, 1, 2, 3. And so the rank of Q, just to prove this, okay. Otherwise, we could probably just pack it up here and call it a day. So we can see that A equals QR. And when we think about this, what it means is that we can get the entries of A from Q thanks to some transitional matrix. And we know that Q is mutually orthogonal to the basis of A, and R, then we can say, is more specifically an upper triangular matrix. And so what I'm going to do is scroll down a little bit and show you why this is true. And this is going to get a little hairy, but it will prove to you that the column space, if we look at this, is this going to be the same as the row space. And scrolling down, we have the entries. We have this vector is going to be one of these vectors plus 0 of this vector plus 0 of this vector. And so that's the first column. And we can see that the third column, I did this as the third column, so you can see that these entries are being used as the coefficients for this vector. And we already kind of know this. We already saw this. But what you is kind of staring us in the face to get from A to Q is this R. And we can think about this R as being this row of A where, and we say it takes one of these rows plus 0 of these other rows, and we can see that 1, 2, 4, 1, 2, 4. And so when we do this second row, now we have 0, 0, 1, and we have one of these rows, 0 of these, plus 0 of these, plus one of these rows, and we see 0, 0, 1, and we have 0, 0, 1. And so one of these, this last row can be thought of as 0 of these rows plus 1 of these rows plus 0 of these rows. And so that just proves to you the relationship between this fact that the column space is equal to the row space. So we can say that the rank of both are equal, and we've seen that. And now that we've manually composed this equation, we can actually take a look at what it would be like to use the built-in. SymPy does have one of these. We would say QR is equal to A decomposition. Oh, I'm sorry, QR decomposition would help, huh? And so when we look at this, we can say R, 1, 2, 4, and we see that. If we go back to the equation, R is 1, 2, 4, 0 through 6, 0, 0, 5, as we've already done manually. And to prove that this is real, and let's look at Q. Obviously, we know what Q is going to be, and we know what A is going to be. And so A is this matrix. Q is this orthogonal matrix, this orthonormal matrix, orthonormal to the basis of here. And R is an upper triangular where all of the entries where I is less than J are 0. And this tells us how to get this A matrix to this Q matrix. And we can see that over here, it's just a simple row swap. These two are swapped rows. And we can prove this to ourselves by doing what? We can actually take the dot product of Q2, and we can take this one as well. And so when we run this, or you should run these one by one. So this is a good example of how to find Q, which is an orthogonal basis, and an orthonormal basis more specifically, to A. And we also reviewed what R functions as a quote unquote transition or linear mapping in a way of how to get these entries from Q. And so next time, maybe we can go a little bit deeper into eigenvalues and eigenvectors.